welcome back. We are on to the next session. If you can just move to the seat in front of you, that would be great, so that those coming later can just sit behind. Right, so we're going to have another amazing session. So the speaker is here, and bringing the next talk to us is Tun Shwe, and he's the VP of Data at Quix, where he leads data strategy and developer relations. He's focused on helping companies imagine and implement their strategic data vision with stream processing at the forefront. He was previously a head of data and data engineer at high-growth startups and has spent his career leading T-shaped teams in developing analytics platforms and data-intensive AI applications. So the title of this talk is Moving from Offline to Online Machine Learning with River. So welcome with me, Tun. Thank you.
Thanks so much. I usually just launch into it, but if you're going to clap, I'm going to let you do that. Thanks so much for coming to my talk. So it's moving from offline to online machine learning with River. This is going to be a relaxed session. It's not going to be too technical, because it's usually new for a lot of people to deal with real-time data and stream processing. So I'm going to start off by just taking you through the streaming data kind of technology landscape, kind of like a bit of its history. We're going to talk about the differences between online and offline machine learning, the benefits of online machine learning, why you should take it seriously, and then I'll introduce River, which is an open source real-time machine learning library. So yeah, I had a lovely intro just there. I don't need to say too much more beyond that. My background is in data engineering, so I've been a software engineer for about 20 years. The last 10 years is specifically in data as a data engineer. So I've worked with some interesting stacks, like analytics engineering, most recently with tools like dbt, but a lot of my background has been with Kafka, Spark, Python, Scala, that kind of ecosystem. I've helped a lot of companies as a head of data in the past few years, go in and help them understand their data strategy, help them to determine it, and where appropriate to use streaming technology at the front, just to make life simpler. My areas of interest are around AI and the streaming landscape. Seems like every other day there's a new startup or a new technology getting funded. So there's like so many out there. So I like to stay on top of it. I'm a big fan of the mantra less is more. I like simplicity, and I think like it's human nature to try to find success in complexity. In a lot of the companies I worked at, there would be like a very simple technology stack, and it'd be working really, really well. And given enough time, someone will find a way to make it really complicated, and then it will start working against you. So I think less is more. I think I'm always the person in the room who's going to be like, do we need to add that additional technology? Do we need to do it in this way and add more complexity? And I'm a big fan of getting started sooner. So yeah, with technologies like River, they're quite radical. It's not what most people do, as I'm going to get into here. But you're in this room because I think you have open minds about getting started on something different. So hopefully you'll find it interesting. So let's start at the beginning, like kind of how is data stored? Hands up if you don't know what a database is. Okay, that's good. I've had one hand go up in the past, and it was like, please help that person. So databases, they're stored, you store your data in tables. That's how it works. And then you have records in tables, and you have columns. With stream processing and the streaming landscape, you have this thing called message brokers or message transports. And the analogy there is they're stored in topics. And so the parlance is you will produce two topics, much like you write data to tables. And like you would query data from tables, you would consume data from topics. So that's kind of like how it works. My friend always says the message broker looks like a database that's fallen on its side. I think that's appropriate sometimes, but it's kind of like a message channel. That's kind of like what it's trying to illustrate. This is kind of like the landscape as well to this day. So hands up if you know what Kafka is or have used Kafka. Amazing. OK, yeah, it's about like 10 hands in the room, which is good. So Kafka is something that was started at LinkedIn just over 10 years ago. It was created to solve highly distributed problems with real-time data. And there was the founding team from that team inside of LinkedIn. They spun out a company called Confluent in the top left. And they've been going ever since. They're like the de facto. Like anytime you have enterprise Kafka needs, Confluent's probably the company that you'll find. in the bottom right, you've got Pulsar, which has been going around for about just under a decade, I think. And that has its own way of stream processing, its own API. But all the technologies you see here will implement the Kafka API. So in the bottom left, you have Red Panda. That is a drop-in replacement for Kafka as well. It implements the API, as is WarpStream in the top right. WarpStream's approach is to go completely diskless, like completely use cloud storage as the storage mechanism, so no local disk or anything. And that, again, was radical in the world, so much so that Confluent acquired them last month. The main message here is that Kafka came from a Java landscape. It was created by Java developers, and the API is based around that. There's a bit of Scala in there, but it's predominantly Java. So it's in the toolkit of software engineers, platform engineers, those sort of personas. So Java, that's really what it's about. Just out of curiosity, anyone here write code in Java day-to-day? There's like two. Not day-to-day. There's a gentleman at the back as well. So yeah, it's not such a surprise, right? Because the language of data is Python, right? I think everyone can agree with that. We've got such a mature tooling ecosystem. So why doesn't these tools exist for Python developers so that they can very easily grab data from arguably a very important source of data, real-time data? So a few companies were born out of it, so I work at one of them. We're called Quix. The background of Quix is it come from a Formula One racing background, so the founders there, all smiling because they worked at the exciting race team called McLaren. Like, if anyone's familiar with Formula One, they'll probably know that team. That was a highly critical environment, so they got to Kafka because they tried to write data, like really high throughput data, really high volume data, really quickly to databases, and they found that the databases couldn't keep up, so they needed a way to process that data. And when you're in that kind of environment, all roads lead to Kafka, and that's where they ended up. And so they're able to work in this critical environment where you have engineers. So for example, like with Formula One, you have these things called race weekends, where you travel to a different part of the globe every weekend, and you race on these exotic tracks. And during the race, you've got so much telemetry data, lots of instrumentation, lots of logging data coming in, and you have to react on that data really quickly. You've got different teams, like you've got the pit team who care about things like the tires. You've got teams that look after aerodynamics, the angle of the spoiler, all that kind of stuff. So you've got all these teams huddled around their own respective computers, trying to run their machine learning models, their physics models, and understand how you can tune this car really quickly so that you can win the race. And at the speeds that these cars go at, a second is like many, many meters on a track. So it's the difference between winning and losing. So highly competitive. You'll notice I'm not in that picture. This is probably how I got the job. The joke is always I had pretty decent data engineering skills, but being able to get in a fast car is something I love to do. I think that's what got me the job. So yeah, always do research on your employer. Right, so one of the technologies we look after is QuickStream. So it's an open source Python library. It enables you to do the consuming and the producing to and from Kafka in pure Python. There it is, pure Python. I think it's gone down a little bit since I created this slide because we've started introducing a CLI, which is not written in Python. But for the most part, it's Python. The message here is that it's not wrapping Python around Java or anything like that. So I'm sure a lot of you don't write software and ship it to production immediately. I hope not anyway. I hope that you'll iterate and you test your way there. And as you're testing it, you come across bugs, you want to fix them. You want really nice errors, right? You want to get to the line of code that's causing you a problem. Being pure Python enables you to do that. And you don't get funny stack trace exceptions like in Java. Gentleman at the back smiling. He's like, you could live in that world, but you don't have to. You get the line of Python that causes you a problem. You can fix it really quickly. This is kind of like what it looks like. So we've got this concept of input topics and output topics, so you can build up data pipelines really easily that way. Some of you are probably looking at that and saying, data frames, I know what they are. Who's worked with data frames? So Spark data frames, pandas, right? Yeah, quite a few hands in the room. So we modeled it around data frames. So we have this concept of a streaming data frame. You'll see on that line there that we have created a data frame that is streaming from an input topic. So every time new data arrives in that topic, you'll be able to have that as a data frame. And then from there, it's as you'd expect. It's kind of, you select the columns, you do your projections, you select your data that way, and you're able to transform your data in a pipeline like this. And at the end there, write it back out to a topic. So you can create pretty complicated pipelines. When especially in data science, you would probably have to do certain aggregations, and we support that through things like window operations. So we have a good abstraction on top of the consumer library. Here we've got an example of a tumbling window. So it's a window that is not it doesn't overlap. It kind of just tumbles. And this one is set to 10 seconds. And we have this concept of other nice things like grace periods, because in the real-time world, you can have events that arrive late. Let's say the network goes a bit slow, like that event is created, it doesn't get transmitted in time, it arrives late. So you're able to consider that as part of the window. And we do a sum here, but we support any custom aggregation. So you may be familiar with having an initializer and having a reduce step. You can do that here as well. And that's the open source library. You can take that, you can use that how you want and deploy that, give that to your platform team. But we also have a business around making this all work for you seamlessly without having to worry about infrastructure. So we have a SaaS platform as well, which enables you to visualize this pipeline, these pipelines that you've built, and not have to worry about Kafka itself, Kubernetes, CI/CD, things like that. So it's a one-stop solution to this. So onto stream processing. Stream processing is like the flux capacitor. Like that, that reference is probably getting more dated over time, and I think the way Hollywood's going, they're probably going to remake this soon and bring the flux capacitor to the next generation, but it's the thing that makes stream processing possible. It's the heart of it that enables you to take that data that's being generated and do something with it. So let's go on to what is offline and batch machine learning. So I think with machine learning, when you have a model, you can separate it into broadly two areas. So you've got the inference part, which is when you use the model to make a prediction, and you have the learning part, which is where you're taking data points and you're using it to train the model, adjust the weights in the model. Let's go into inference. So you've got the predictions that are generated from batched observations. So for offline inference, what you would do is, an example is I've worked on recommender systems in the past. I worked for a large publisher that had like millions and millions of users, and every night we would take the click stream of those users, as in what did the user do on the website? Did they click on these articles, these journals, figure out what their preferences are from that, and then use a machine learning model to generate the predictions all en masse. So for all, there's about 100 million users. So generate 100 million predictions for them to give them 10 recommendations roughly each, and then you'd save it in a database. So you've generated all those predictions, saved it in the database. Some other team comes along, I think at like 5 in the morning or something, reads from that database, takes those predictions, and emails them to everybody. So that is an example of offline inference. Let's get on to offline learning. This is probably anyone that does machine learning is doing offline learning for the most part. It's the most common type. It's when you fit a model over static or historical or bounded data. So it's usually a data set that is static or fixed. If you're a data scientist, being a data engineer, normally we'd get a request in, like a ticket that says, right, I need all the data between this week and this week, and then you generate that, and that's your static data. So that's a bounded data set, and that's generally what you'd use for your machine learning. So all those observations are grouped together and processed in one go. So with offline learning, you are fitting a model over that static data. So that data isn't moving. It was data that has been created and generated in the past. You're taking batches of observations at a time. So you need to have all the data that occurred in that period. And it requires a lot of memory. The data normally doesn't fit into memory as well on one machine. So if you're used to tools like Spark, where you have lots of parallel workers, what you do is you break that big data set down into partitions. You partition it by some logic, like you could do it by time, date, whatever, or you can do it by a certain other element that occurs in that data set. And what you then do is have an engine like Spark process that data in parallel using many, many workers. And that's how you take a big data problem and turn it into a small one. And bounded data is really easy to reason about. I think, from my experience, humans struggle with the fourth dimension, to think about the passage of time. It's often difficult in a machine learning context. So what you want to do is get all the data in one go in a bounded way, and then you want to be able to use that to train your data. It's well-established processes and tooling. There's it's the de facto, so you have so many different options for doing that. And machine learning has a long history as well. It came really from data analysis. Like you started off analyzing that data, finding patterns in that data through visualization, and then eventually someone will come along and say, well, if you can answer that, maybe you can predict the future. How about you try and forecast some of this? And that's kind of like where machine learning was born. You're figuring out the patterns just through being able to visualize it in a different way. And this fits, I say 99%, but that's a made-up number. It feels like 99%, like most people who do machine learning do it in this offline fashion, and it just works. And so through the history, you've got data science and batch processing deeply intertwined. So what is online machine learning? Before I go into that, let's think kind of conceptually what the journey of data is. So it's generated in real time. So I've got a nice AI-generated image of a robot in a factory. That tends to be one of the main use cases for real-time data. So that data is being generated. So let's say the vibration, the temperature data of that robot is being generated. So data is generated in real time. And it typically stays in motion. It's transmitted to something like a message broker rather than a database, and then it will stay in motion. And then it's pushed from there into a database, into an at-rest state. So you might save it to object storage like S3, or you would save it to a database. So it gets kind of pushed into an at-rest state. And then at some point in the future, a scheduler will kick in, will read that data, and then you process it in batches. So the question is, why don't you deal with that data whilst it's in motion? As that robot arm's generating data, why wouldn't you look at it then? Why wouldn't you process it then? And the pushback I've always gotten from companies that I've worked at is it's complex and it's difficult, right? Like I said, thinking in fourth dimensions is one thing, but how do you deal with infrastructure that has to deal with so much data? There's not a factory with just a single robot arm. There's in some factories there are hundreds and there are multiple plants, so you've got such a high volume of data. It's complicated, it's difficult, right? So let's do the same thing with online machine learning. So we've got real-time predictions now for online inference. So you're using the model to make the predictions at the moment that you're making that request, and you're fetching the necessary features at that time of request. Obviously, fetching features needs to be blazingly fast, otherwise you might have a user on the other end waiting. You don't want that, so you would use other specialized, databases known as feature stores. Anyone familiar with feature stores? Okay, a few. Okay, go look them up. They're really, really useful. So feature stores, in a nutshell, help you to, features, let's say, let's define them first, are the inputs to your machine learning model. They help you to, picking the right features is directly correlated to the predictive power of a model. So you want to be able to retrieve those, you want to generate them correctly at the time of training and be able to fetch them at the time of inference. So this is another layer of indirection with your data that helps you to keep everything consistent. And online learning, also known as real-time training. It's fitting a model over streaming data, as you can imagine, and it's learning one observation or data point at a time. So that's the key difference between batch and online. You're taking one observation at a time. And with online inference, it's what most people mean when they say they do real-time machine learning. So when I go to conferences, I talk to other practitioners. I say, do you do real-time machine learning? They'll say, oh, yeah, we do that. And when you drill down, what they're actually doing is online inference. And most people do that. So you have an API that the machine learning model will hit at the point of request time, and it will get the prediction out. That's actually what's happening. Inference is straightforward to do. Again, so much tooling is available to make that happen. And it works with batch models, of course. So you train models using a batch approach. You can use them for online inference. And yeah, it has a mature tooling ecosystem, so many different frameworks. All the major cloud providers give you a flavor of their platform that will enable you to select models, retrieve them, do CI/CD, all that stuff. And with online learning, this is about fitting a model over streaming data. And what it's actually doing is it's learning incrementally, one observation at a time. And this is something that most people don't do. You can see a snippet of the code there. You would take those observations and you'd start learning from them one at a time, rather than in batch. So you can see event 1, 2, 3, 4, and 5 will occur at different times, and you would make your predictions like this and learn this way. So with online learning, not all algorithms are suitable. So taking the algorithms from your batch world. You can't just immediately transplant them into online use cases. That's not how it works. They naturally work really well with unsupervised methods. So with the supervised methods, you need to have a bit of thought around how you design your pipelines, how you design your systems, because the ground truth, the labels always come in later. An example would be, I think for something like some sort of click propensity model, like over time you would serve up these offers, let's say, and then over time you'll realize the user does eventually click on this, and that's when your actual ground truth will come in saying like this was an effective recommendation. So if you're thinking in fourth dimensions, it's kind of like that's how actual machine learning in the real world works. It's an event stream. It's something you're waiting for to see if something happens, and when it happens, you want to make sure that you capture that data point and incorporate that back into the model. And since data is streamed in, there are many unknowns. The surprising thing with online machine learning is you just don't know what you're going to get. You just kind of accept what you get. So features will appear, they'll disappear. The cardinality changes over time. You just don't know. You just kind of accept it. And you contrast that with batch learning, where the first thing you'd do is you'd do exploratory analysis on it, and then you'd figure out the cardinality for these fields. You'd do all of that. Not entirely possible with online learning. You just don't know what you're going to get. And the benefits, let's go through those. The fact that you don't know what you're going to get is part of its strength as well, because it will start being able to adapt to new data that comes in, like new values, new cardinality. It's able to adapt to new data and trends. It's something that you would see, I think during the pandemic, all the smart online e-commerce stores like Amazon, they would figure out, okay, loads of people are suddenly buying masses and masses of toilet paper. Like, what's going on? Like, no one ever told that model that a pandemic was happening. It would just figure it out and go, right, so we're going to suggest other things like Snuggies and blankets and things, that you would enjoy in the home, like when you're not leaving the house. So, like, the smarter systems would figure out how to adapt that way. The fact that you're looking at observations one at a time and learning from them means you require way less CPU and memory. You don't need a system like Spark anymore to partition the data and take a big data problem into a small problem and turn it into that small problem, because you already have a small data problem. And historical data is not needed. That's another cool thing. People always ask, and in the Q&A, so I'm just going to answer that for you now. How do I get started? You can get started anytime you want. You don't need historical data whatsoever. The weights kind of start off evened out or zeroed out, and you learn from there. So this is great if you have little like hobby projects with like Raspberry Pis. I've got one at home which is environmental monitoring with environmental sensors. I could just start running a machine learning model like right now and start learning over time, and it will just adapt to my environment, and it will figure out over time like what the correct weights are. With real-time machine learning, it doesn't require retraining. So normally, you've got to run a pipeline that will retrain your data. So as you finish training your model, you probably have new data points that have come in that you have not yet incorporated into your model. So at regular intervals, you need to kick off a big retraining step or figure out a way to incrementally add the new data points into your model. It's resilient to model, or in this case, concept drift. So concept drift is when the underlying distribution in the data changes over time. So the changes are in the relationship between the features and the target variable, which means that there's a degradation in the predictive power. So it's immune to that because as it's looking at a single data point at a time, it can just figure out things are changing and adjust the weights accordingly. So you have to think of the model as a stateful, ever-changing object. It's something that always stays on, is always watching, is always listening, is always learning. Much like the human brain, right? And these are the sort of use cases you unlock. Like a lot of the companies I work with are like they have lots of sensors, they have telemetry data, so predictive maintenance is a big one. It's really beneficial for these big factories with swinging robots and things that can cut like various sheets of metal and things like that. Like having predictive maintenance is extremely key for hitting your targets, like your company's policy for targets around safety. Like you don't want these huge machines to malfunction. There's also like thinking about those machines as well, I can think of one of our customers who has like CNC machines. So they will take like a big sheet of metal and they will machine out different components for, let's say, like white goods, like fridges. So it's able to use machine learning in real time to figure out, right, we're generating this much wastage, we need to cut in this way to reduce that waste. So it's able to unlock really interesting use cases like that. I think dynamic pricing with Uber is one most people will be familiar with if you've ever used like taxi shares. And we're starting to get some traction in gaming as well around anti-cheat systems, because normally what you get are like for games like Call of Duty and Counter-Strike, you've got this thing called an aimbot. It's an aim assist device that helps a player find like people on the map really quickly and basically kill them as soon as they appear. So these anti-cheat systems, these cheat systems tend to have a way of working. Like they'll immediately find like where the other players are on the map, and from that you're able to adapt as the cheater changes like the algorithm or changes. Oh, I think I kicked off Siri, did I? Anti-cheat. Okay, so that's anti-cheating. So often the conundrum then when I talk about streaming data and streaming technology is, right, so there's batch, and there's streaming, there's offline, and there's online. So can I just take streaming and make everything streaming, just replace batch completely? So I made this meme to illustrate it and make it really easy to understand. So do you choose batch or streaming? You actually choose both. There's a third option. And the reason is because they're complementary. Like one does not replace the other. You should use them both at the same time. It's great to use the stream for current context, because it will always be listening and reacting to changes as they happen. As you generate new data, as a user clicks around your website, that's all current context that you could be using. Use batch for the historical. Batch, having all the data in front of you and running your algorithms over that just generally has better accuracy. Like when you put them together side by side, that's the benefit of blending the two. Batch will always be accurate because you have all the facts, right? So the model is able to take those facts and create a better model. Most teams do try to fit streaming into a batch system, because the batch system is the one that already exists. Let's add streaming to it. But I find it's much easier to kind of rethink how you do absolutely everything and fit batch into a streaming system. And I consider batch to be a specialized subset of streaming, because you have that batch, like that fixed data set, because that data was generated in real time, and you've just kind of collected it and kind of like boiled it down to that. The benefit of events being the foundational unit in online machine learning is that the events can be rewound back. You basically have a play-by-play step of how you got to the current data set. So you can rewind that using technologies like Kafka, which it stores like a retention. So you're able to replay all those events back in the correct order that they came in, and you can recreate any historical state. So it's like super powerful. This is the sort of architecture I'm not recommending. This is the old way of doing things. So you have a data source where you have a real-time layer that you've added to a batch layer. So when you get these queries in, you have very real-time, like extremely fast queries that need to be answered straight away. And you've got like kind of batch queries that are asking about historical data. The one in the middle is the fun part, where you have a mixed query that wants a little bit of this, a little bit of that, and we call that enrichment in our world, where you are trying to enrich some of the historical data with the current data. An example would be, let's go back to clickstream. You get a clickstream of a user clicking around. You would normally transmit that data with just an ID, but you might want to know the geographical location of that user. So you might want to enrich that with data from a batch layer. So you would access a database that would tell you more about that user's profile. And then at that point, you could you could create applications that use that geographical information to serve like appropriate ads or what have you. So the problem with that Lambda architecture is that you have two different code bases that need to sync and be coordinated for releasing. It's normally code duplication, and that creates complexity. We all know I don't like complexity, and we shouldn't go for that. And you have to validate these algorithms to make sure that they align. And again, like with the mixed query, where do you read from? If there are delays in batch, like do you read from the fast layer? Like what do you do? Like it raises a lot of questions around your system design. And with that double infrastructure, you have double the monitoring, double the fun. And so you want to avoid that. And this is the one that I do recommend. It's one called Kappa architecture. And it's when you take that data source and it just comes in and you have a real-time layer. But what you do is you sync or you write that data to a storage. And then you have this concept of a real-time app that's always processing that data as a stream and then storing it in its own way. And then you have another layer, which is your batch app layer. And that will, keeping it like that means that you're always considering real-time first and you're trying to service it. If you can't use that real-time data, you go and you fetch it from the historical data. You've got a single core technology stack with a single entry point, much simpler. And it's real-time, and it's possible to recreate that historical state. So this is fantastic for testing because you can play back events and try to recreate steps in a timeline. Like, let's say if things went wrong in a given day, you're able to recreate that and like try and understand that better and debug. And you don't need to re-architect. So when there are new use cases, so normally what happens that I'm seeing out there is you'll have a fully working batch system, and then somewhere along the line, someone will say, I have this use case where this has to occur in pretty much real time. How do we do that? And that often requires a re-architecture. But if you have already thought about streaming in your design, you would already have something closer to a Kappa architecture. That means when you have new use cases, you're just scaling out. You're not introducing like, additional complexity. So using them both together helps you solve these cases. So you've got offline, which solves most machine learning problems, as we know, and you've got online, which solves problems where current context is important. And you would probably need both. I love the product managers that go out there and they find those use cases. So let's talk about some of these libraries that enable that. So we've talked a bit about the enabling technologies in that streaming ecosystem. Let's talk a bit about the actual machine learning, the online machine learning that happens. So you've got Cream, first of all. It's a project that started with a mission of providing pure online machine learning models. And then you have Scikit Multiflow, which was a project that was specialized in online machine learning models, but they also had this side focus on models that would be able to do things in small batches, like micro-batching up, like your observations. And there was a lot of crossover in these two missions. So the project leads got together and they determined that the focus should solely be on online models, the models that learn one data point at a time. And so they merged. And that was how River was born. The concepts around River and its benefits are, it's got a really great developer experience. It was heavily inspired by scikit-learn. Like every data scientist knows what scikit-learn is. Some are still using it today. It's just like the classic way to learn. It's a great, easy way to implement machine learning. It's great for general purpose ML tasks, so it can do all the things you would expect as well. And there are loads of different models supported. I work a lot with anomaly detection, time series forecasting, but it supports so many different types of models. You've got, like, I'm going to list a few off. You've got, like, for the anomaly detection, we've used things like the Gaussian scorer. There's half-space trees, one-class SVMs. There's, like, loads of different things there. For time series, you've got Holtz-Winters. There's a lot of other options there. The models cope well with concept drift. They actually have a drift package as well. So it has support for adaptive windowing in there and the page-Hinckley method. And the last one I've saved for last because this one kind of blew my mind a little bit because of how we're all used to dealing with the data in batch for machine learning, is that everything's a dictionary. Everything's like in plain text, it's key values. So let's have a look at some of the data sets that River gives you out of the box. So one of them is New York Taxi. So here it's about the duration of taxi rides. So it's really nice to just be able to import this data set in and start working with it. If you look at the actual data set itself, you can see that you've got things around duration, etc., and you're able to start like building a model that will predict the duration for these trips. Here's another one. This is a fishing data set. And again, you'll see when you initialize the model, you get things that are like zeroed out, and then you start like incrementally, as each observation comes in, you are making new predictions, and as ground truth, as the labels come in, you're adjusting these weights. Everything being a dictionary is really cool because it makes the features explainable. In offline machine learning, you're often using arrays and vectors, so you're using things like NumPy arrays. And when you use NumPy arrays, you just don't know what's in there because they're all in numerical representation. And also you've got to preserve the order of the features because it's an array, it matters. With this, you don't have to worry about that. You also don't have to worry about any sort of numerical representations like vectors because you can't benefit from things like vectorization, and there's no such thing as matrix multiplication in this world because you just don't know what features you're going to get. You don't know when they're going to disappear. It's just one of those things. It's kind of Zen. You just accept that things happen. Dictionaries are native Python data structures as well, so like extremely explicit. They work really well. And yeah, the best part is you can actually just read what the actual fields are. Try doing that with offline machine learning. It's often difficult. You need to go a step back. And these are what the models will actually look like. You see some with some weights already prepared there. I mentioned that the online model is a stateful object as well. And since in River, the models are all dictionaries, what you do is when you get a new observation, you just add it as another field to the dictionary, and you'd maybe zero it out or try and initialize it in some way, and then that's how you'd build up this model. The fact that it's a dictionary is really cool as well because you don't have to pickle it or do anything funny with it. You could literally save that JSON somewhere, and that can serve as your checkpoint. So as you're building out your online machine learning model and you're evaluating it, if you see any sort of degradation, you can easily roll back and try maybe a different ensemble, a different bandit, different type of model. And this is kind of like the API. You predict one and you learn one. You can see it's reminiscent of scikit-learn. And you've got, here's an example using logistic regression. And you don't need to compute your own metrics. That's another thing you don't have to worry about. So this is an example where you would have to worry about looking after your own metrics. So you've got your predictions, which you need to store, and you need to store the actuals, the ground truth, as they come in. And so it's a bit cumbersome doing it this way, but in River, you have this concept of metrics. So you can see there at the bottom, when that ground truth comes in, you can update that metric. I'm using here an accuracy metric. There's lots of other metrics you can do, but for accuracy, it's just the percentage of ones that you got right. And I'm printing out the accuracy. So this is a really neat way of figuring out how to have a better model over time. And you've got scalars, you've got composable pipelines. So they have created a pipeline there with a scalar. I'm just using a standard scalar, but you can use things like min-max scalars. So let's say you needed to scale your data so that it was between 0 and 1. You've got scalars for that, so that's something you might want to use. And that's how you can do things like this. When you get around to evaluating, you can use progressive validation. Progressive validation is when the target is revealed to the model after it's made its prediction. And to test how well the model performs in production, what you generally do is you introduce a delay so that the ground truth label comes in sometime later. And that's kind of representative of real life, because like with the clickstream, you just don't know until some time later whether that recommendation was clicked or not. So this is a really good way to think about it, because it's very much like real life. And yeah, it's got a nice printing function, so you can just kind of simulate if you deployed that model with this data. This is kind of you can kind of just see how it changes over time. And for my last few slides, I'll just go through just kind of some of the things that you can find with River. They've got so many different types of these things that they call recipes, so you can get started really quickly with hyperparameter tuning, active learning, things like that. So it's quite an involved project. It's been going on for a few years now, and so many different use cases. The thing I always like about this GitHub project is when you go there and you go into each one of these sections, it's usually a different author. So it's a person who either was an academic or had applied that in their work. So they're a specialist at what they do. And these are the sorts of people, these specialists, that are contributing to the library. I mentioned I worked a lot with anomaly detection, so yeah, I use the Gaussian score a lot. You've got other things in time series, like forecasting. One thing that we're seeing really popular are half-space trees. They're a type of isolation forest where the anomalies happen quite far apart. So that's really good for things like predictive maintenance for machinery, because the failures don't happen so quickly. They happen after long periods of time. So it's half-space trees are a really good technique for doing that. Yeah, and when I last gave this talk in June, it had much lower numbers. I think it was on like 4.8K stars, so you can see it's something that grows over time. It's a library that enables a lot of this stuff in machine learning. It's radical. Not everyone's doing it, but you're in this room because you're curious about it. I hope you'll check it out and try it out. And as I mentioned, you'll need some other enabling technologies like Kafka. Hopefully, you'll also use Quix streams as well, which will bring Python, which will bring real-time data to the masses of Python developers out there. So yeah, you can hit me up at any of those locations. I'm everywhere in those 3 QR codes. So if you have any questions, happy to take them now. Otherwise, connect with me later and ask away. Thanks so much.
If I wanted to try and play around with...
Oh, should we get a microphone? Oh,
no, it's all right.
OK, go for it.
I'll talk louder. If I wanted to play around with River myself at home, could I just go on GitHub and...
Sorry, we
Oh.
wanted to record it.
Oh, sorry.
Oh, OK.
So if I would like at home to play around with River and understand how it works for myself, would I be able to find information in that GitHub repository about how to get started, like considering I know nothing about it?
Correct, yeah. We all start somewhere. I mean, yeah, this is a great library because it really helps you to start from the beginning. I mean, it assumes some prior knowledge of data science and just machine learning in general. So if you have that, you'll be able to get started. You can see the APIs very much. It has scikit-learn as a dependency in there as well, but you can see the API was designed to be very familiar to those who come from that classical machine learning background. So if you are, I think you'll have an easy time. But yeah, there's so much documentation.
I look forward to playing with it.
Yeah, and it being open source, I always recommend anyone who's looking at it, like normally when I'm reading other projects that are open source, I usually kind of like fork the docs repository, and as I'm reading it, if I find typos or ways to improve it, I usually create my contribution right there, and I open a pull request. So that's a habit I'd love everyone to get into, because that would just incrementally just make these projects better. And some of these projects, they do their best, but they're built by those who don't have English as their first language. So you could just very easily just like clean up syntax and kind of typographical errors. So I always do that. And you'll see me in the River Library doing a lot of that stuff because I'm not quite the expert at some of the models. So I'll help in whatever way I can. I think anyone can as well.
I had my curiosity around the real-time ingestion. So the architecture, infrastructure-wise, where click streams comes into the play, the Python script we saw. How does that really look like? Is it a Lambda function? Because if I'm actively ingesting and responding to the streams I'm getting, how does that really look like in an infrastructure-wise setup?
Yeah, that's a really good question. So with streaming applications, so something like if you're building an application in Quix streams, it could be a step in the pipeline. So it's reading from a topic and it's writing out to another topic. By its nature, you just don't know when that data is going to be generated or changed. So it's an always-on function. So it's, I mean, you mentioned Lambda functions. I presume you're referring to AWS's Lambda functions. So when I said Lambda architecture, that's not the same Lambda. It's more about the Greek letter Lambda. But for those who don't know, in AWS Lambda, it's a serverless component. You literally just write like handler logic. And the handler logic says when new data comes, I take it in this representation, I do stuff with it, and then I write it out somewhere else. And that's just how Quix streams, that's how a lot of these stream processing applications work. There's an input, it's reading from somewhere, and generally it's writing out to something, a database or back into a topic. Like when I showed the slide with Quix streams, you'll see like all these boxes with arrows in between them. We generally will build up a stream processing pipeline that could be like pretty long with loads of different steps. And at each step, you're writing back to Kafka in a topic. So you can chain it up that way. The beauty of that is normally someone will request a copy of that data. They'll say, you'll get a ticket that comes in and says, that data on that topic, I want that to appear in this table, in this database. Go. And it's super easy to do that. And it's not much of, you don't have to scale that out too much either, because like Kafka's just built for this kind of scale already. So I find that is a much more useful distribution mechanism for data. But to answer your question, yeah, it's an always-on application that's always running. It's essentially running in a loop.
Sorry, yeah, I have a quick question about feature engineering.
Okay.
Obviously, with like offline learning, it's quite straightforward. Feature engineering, seeing how those metrics might compare against like a baseline without doing any feature engineering. How would that look like for online learning, or is that quite difficult to do?
It's not difficult to do. So I think I alluded to one of the famous quotes in computer science, like all problems can be solved by another level of indirection. That level of indirection is usually a feature store. So if you're doing real-time feature engineering, even when you're doing offline machine learning, you want to capture those features correctly, and you want to make sure that when you're retraining a model or you're creating a new version of the model, that you have versioning around your data, right? So you want to be able to capture those features and put them somewhere. So I would say you should be using a feature store then, but certainly for real-time feature engineering, you definitely want to be using a feature store, because when you're doing the actual online model inference, you want to be able to get those same features out that were generated in your feature engineering during the training steps. Does that make sense? Yeah, it's a different way of thinking, especially if you've never used a feature store, but it's literally another level of indirection where you're centralizing your features during training, and then when you switch to online, you use the same approach. Okay, we can talk after as well. I'll explain a bit more. No worries.
Do you have some version of gradient boosted trees? I saw hefting trees, something like that. I know they are for online learning.
Yeah, check in the library. There are various boosts in there, but I can't remember all of them off the top. But yeah, it's a pretty big library, and if there isn't one, you can definitely write and contribute one.
Yeah. Second question is, some models take a long time to train, and if you do some, let's say, incremental training, you might be stuck in a local minimum of your objective. Is that something, I mean, how do you tackle that kind of issue?
Right, yeah. Yeah, like I mentioned, you've got to be realistic when you're deploying online machine learning. Like, it doesn't work in certain scenarios. Like with things like concept drift, that is a great candidate for deploying online machine learning there. But for some of the classical challenges that you would have, you probably should be doing it in an offline way, because you have all the data and you're able to change. Like you can do your feature engineering in multiple different ways because you just know what you have. When you don't know what you have, that's when online comes into play. So things like boosting, like you would need to know like the ranges of your data. You would just need to have your data set already. Boosting in an online way, that like I'm not sure. Like I've seen there were some models in there. I've never used them, but I'd be curious to know like if you find anything interesting. Thanks.
Really good presentation, by the way.
Thank you.
Kind of linked to the last question. How are you doing, online validation? Because, I mean, with this sort of online approach where the data's coming in, it's streaming in, you're pretty much just doing, you're doing prediction on the fly. So how do you validate what's been predicted? Because there's no real model per se. I mean,
right.
I saw in the code that the model then comes later. So how do you validate what the Y hat is?
Okay. Yeah. So because it's an ever-changing model, like the model always exists. Like it can start off like very untrained. Yeah, exactly. So you can start off completely zeroed out. That's a common approach. Yeah. Like the weights are all zero. Or you can start off by, if you have a classifier, you can balance everything evenly. So you can start there, and over time it'll adapt. So how you validate it? Yeah, it's a really interesting question, because I mentioned on my slide about progressive validation. That's when you kind of, generally like how you would have a holdout set, but in this case, you're intentionally holding it back and then giving the ground truth later, so that metrics package will go, like you would write the code to say, okay, now we have the ground truth, and here's what we predicted, here's the actuals. It will then use that to adjust the weights on the fly. So yeah, it's one of those things that you have to, like, once you've deployed a model, you have to keep an eye on it. You have to do that progressive validation. Some of it does happen offline. Kafka is a great enabling technology for that because it's event-based. Its data is captured as events, so you can just replay things again. change. So an approach might be if you're using like a bandit, you've got like an ensemble of like multiple models, and you have something that kind of is able to pick the best one out of those given the circumstances or your inputs. If you deployed something like that, you could have models like dictionaries essentially of each model. And as you're validating it, if you see some degradation, you can either roll back and try something else, or you can route it to like a specific model. So you can build really complex systems, like if you start amassing knowledge around which model works based on the data. But as you know, it's always based on the data that comes in. This is just like another toolkit to go alongside your offline machine learning that just helps you completely with current context. Obviously, after the fact, hindsight's 2020. After the fact, oh, we shouldn't have done that. That was probably the wrong move. We should have tweaked it in this way, and that's natural evolution for online models.
Okay, thank you very much. Thank you.
Thank you.
All right, thank you very much.
Oh, great, thanks.
Thank you.